We have all sorts of degrees of freedom of pose. Yeah, that was cute, I know, right? So even though it's just a person can move in many shapes, although I can move in many fewer shapes than I used to be able to move. And there's so many pictures, right? There are billions of images indexed by Google search. The last number I could find was that in 2011, 6 billion photos were being uploaded to various things per month, okay? There was 1 billion camera phones sold last year. Okay, so they all take pictures. And another interesting indication of the complexity of recognition and of vision in general is how much of your brain, and my brain too, by the way, is devoted to visual processing. There are different estimates, anywhere from a quarter of your entire cerebral cortex to a half. And it's the cerebral cortex that sort of distinguishes you from an awful lot of other mammals. So the recognition, the ability for you to manipulate things so well visually seems to be two things. Very intense, right? It takes a lot of wetware in order for you to do it. But I guess evolutionarily it must have been very useful because you devoted an awful lot of wetware to handling this. What currently works? Well, actually, let's talk a little bit about what used to work. Well, still does. What worked a while ago and what's working now. So what worked, sort of say, yesterday? Okay, yesterday being proverbially not today. All right. So things like reading license plates. Well, that's pretty easy because it's a fixed font. Zip codes, numbers on checks. Those are getting much better, and handwritten recognition of digits has gotten pretty good. Fingerprint recognition. The analysis of those patterns, because the patterns share certain types of characteristics, and we could find those characteristics. Face detection, but you'll notice that here the thing knows who I am, but it hasn't yet figured out who Megan is, right? Today we do recognition. By the way, these days, typically when you pop up or put an image, let's say, into Facebook or some other thing, it'll suggest to you the names of the people that are there. And that means that it's found the faces, and it's also recognized who they are. Now, it doesn't search its database of everybody. It only searches your friends, right? So it doesn't have to try to recognize this as anybody on the planet, just the 5 friends that I happen to have, right? So then you might ask, well, how does it know the picture of those friends? Well, other people have tagged Megan in images. Every time you tag an image with a person's name, you're actually telling Google or whoever, or Facebook or wherever you're doing, how to recognize that person. So without making it sound nefarious, it is the case that every time you tag somebody else in a picture, you're making it that much easier for computers to find that person in other images. You are teaching, you are not tagging, you are teaching the system what Megan looks like. So just think about that every time that you identify people in an image. We've actually talked about SIFT features and using the location of SIFT features to recognize objects and, sort of flat texture things like the book covers. All right. Now, what just happened, this is GoogleNet 2014, which was part of a competition. And you can see here that given this image, okay, it labels the monitor, the bookshelf. It even labels this, it says domestic cat. And it looks to me like this cat is jumping in the air, so that's pretty cool. What makes this picture hard, of course, is the very intense color variation. So it was able to find, just basically through the color and texture, because that's the only thing that's there, the fact that there were oranges and bananas there. So this is a pretty intriguing result. And then here's a result that calls into question the importance of context. And maybe what it means is that context doesn't matter when things are very clear, all right? So I love this picture. I'm not sure you can read this, but it says hat with wide brim on the top, and it says dog on the bottom. Now, I don't know how many pictures there are of dogs with hats and wide brims wearing them. What scares me is there might be tens of thousands because people have way too much time on their hands or something. I don't know. But it is an impressive result that it was able to recognize the hat on top of the dog, which you have to believe is not a likely position for a hat. So going forward, these days, much of strong label recognition is really machine learning applied to patterns of pixel intensities or features. And to cover this, as I said, would require a deep understanding of machine learning and a class or 17 of them to learn that. So instead, what we'll do is we're going to focus on sort of two general principles called generative versus discriminative methods and their application and the representation used in computer vision. And then we'll spend some time on activity recognition from video, because why recognize pictures when you can actually recognize activity? And besides that, it's how I earned my tenure. All right, talk to you soon. All right, welcome back to computer vision. This time we're going to start sort of on some of the small technical details of doing recognition. Remember, we said that recognition is mostly going to be some form of a classification problem, and we're going to look at some methods and some representations. So today we're going to start with what we talk about supervised classification. In fact, almost everything we're going to do is going to be in the supervised domain. So in the supervised world, basically I give you a set of label training examples, and the goal is to come up with some function that if you give it a new example, it'll generate the correct label. So using the handwritten digit recognition as a example. So here we have some training examples, right? We've got a bunch of 4s and a bunch of 9s, and you'll notice it's not trivial, right? Because these 4s, could have been a 9, but no, they're actually 4s. So what I want to do is I want to come up with a function such that if I give it some novel input, I give it something that looks like this, it's going to say what? Is it going to say 4 or 9?
9.
Very good, very 9. Megan's been paying attention. So the question is, how good is this function that we build in order to do the classification? And you can't really answer that until you tell me what good means, all right? And what good means two things. First of all, what kinds of mistakes does our classifier make? All right. And for each of those mistakes, sort of how expensive is it to make those mistakes? And when we build a supervised classifier or supervised classification, since we know what the desired outputs are for a given set, and then we can run the thing as we're designing it, what we want to do is we want to minimize the expected misclassification cost. Okay? We want to make mistakes as infrequently as possible, and the more expensive a mistake is, the less often we want to make that particular mistake. All right. To do this, to handle classification, there are two general strategies. The first method, which is referred to as generative, you basically use your training data from class A to build a model of class A. Separately, you build a model of class B. You build a model of class C. You build a model of class D. And then when you give a new example, you say, well, does model A explain it better, or model B, or model C? Whichever one explains it better, that's the one I pick. And it's referred to as generative because the idea is that I have a model that describes sort of all the different possible things that would be of class A. At least that's the hope. Or you can even think of it as generating a set of examples that are class A. The other way of doing it is referred to as discriminative. Discriminative says, well, here's A, and here's a bunch of things that are not A, and let me learn how to discriminate between them. Okay? So I'm not going to worry about modeling what all of A is. What I want to do is, if I only have A's, B's, and C's, I have to look at how would I discriminate between A or B's and C's. Or I could also do A versus B, A versus C, B versus C, and learn those. But the discriminative approach focuses on learning the boundary, the separator between our categories. Today, what we're going to be doing is talking about generative, and then we'll move on to discriminative in a couple of future lessons. Let's talk about the generative method. And like I said, we're going to be given some training examples, and we want to predict the labels, okay? I need a little bit of notation because we're going to do a trivial amount of math. This little notation, 4 to 9, means an object is really a 4, but I call it a 9. We're going to talk about the costs or the loss. You're going to see L for loss. You know, what's the cost to me of calling a 4 a 9 or calling a 9 a 4? All right? And one of the things we're going to assume for the rest of today, and it's really not a big deal, you can factor this in or out, we're going to assume the cost of calling an X is 0. Okay? So nobody gets upset if I call a spade, so to speak. So let's consider the two-class binary classification problem. Remember, we just had 4s and 9s. So we have two kinds of losses, all right? So that's what this L means. And L of 4, 9 is the loss of classifying a 4 as a 9. And conversely, L of 9 to 4 is the loss of classifying a 9 as a 4. Okay? Pretty straightforward. Risk is your expected cost. Okay? So if I've got a particular strategy, S, classifier strategy S, we want to talk about what's the expected loss, all right? And for our 4 and 9 example, the risk of our strategy is what's the probability that I'll call a 4 a 9? How often is that going to happen, okay, using this particular strategy, and I multiply that by whatever the loss is, the cost of calling a 4 a 9, and what's the probability of calling a 9 a 4, and what's the loss when I call a 9 a 4, all right? And that's the risk. And the probability is, 15% of the time that I'm running this thing, 15% of the times a 4 is going to come up and I'm going to call it a 9. Okay, that's what probability of calling a 4 or 9 means. So this total quantity, that's what's referred to as your risk. And remember, what we want to do is we want to minimize the expected risk. So here we're going to work through this simple example again using our 4s and 9s. We're going to assume that we have some feature that we're measuring x. It's typically a vector, but I'm going to show it here as a scalar. So x goes from small x, so little x, to big X. All right? It's changing values. Clearly, all the way to the left, I've got more 4s, and all the way to the right, I've got more 9s. At the best decision boundary, okay, and that's what's indicated in red here. At that boundary, if I call it a 4 or I call it a 9, it should cost me on average the same. Because in fact, if calling it a 4 would be less risk than calling it a 9, I'm going to move that boundary this way. And if calling it a 9 is better than calling it a 4, I'm going to move the boundary that way. So at the best possible boundary, the expected loss is the same regardless of which label I announce. All right? So if we pick the label 4, okay, at that boundary, okay, then the expected loss is what? Well, it's just what is the probability that it's really a 9 and that I call it a 4, the cost of calling it a 4, and what's the probability that it's really a 4 and the loss of calling it a 4? Well, if you remember we assumed that the loss of x to x is 0. That is, there's no cost of calling a 4 a 4. Well, that means that this just reduces down to, well, if I'm at this location x, what's the probability it's really a 9 and the cost of calling the 9 a 4? That's the expected loss of saying 4 at that location. Likewise, what's the expected loss if I say 9 at that location? Well, symmetrically, it's just what is the probability that it actually was a 4? And what's the loss of calling a 4 a 9? Okay, so those are the two different values, the losses that I want. Now, remember we said before, at the best decision boundary, either labeling a 4 or labeling a 9, the expected costs would be the same. So the best decision boundary is the x such that the probability that the class is really a 9 times the cost of calling a 9 a 4 will be equal to the probability that it's really a 4 times the loss of calling a 4 a 9. When I set those two values equal, that's the x that I want for my decision boundary. What that means is if I'm going to classify a new point, I'm just going to look at these values, right? At some new point x. What's the probability that it's really a 4 times the probability that I call a 4 a 9? If that's greater than the probability that it's a 9 times the loss of calling a 9 a 4, if that's true, I'm going to call this thing a 4. Otherwise, I'm going to call it a 9. What I've got plotted here in sort of a notional plot, this is a expected loss, right? On the left-hand side, that's the probability that it's a 4 given an x times the loss of that it's a 4 and I call it a 9. Over here, this is the probability that it's a 9, but I actually called it a 4. And the decision boundary is where these values are equal to one another. And of course, what is hard about this? Well, knowing what the losses are, that's easy, okay? You just tell me, right? You tell me how expensive is it for me to call a smart person not so smart versus calling a not so smart person smart. Well, probably has something to do with their stature, okay? So my losses might be asymmetric, or my losses might be symmetric. Like I'm doing zip codes, right? And if I call a 4 a 9, it goes to California, and it should have gone, what starts with 4? What zip codes start with 4? I have no idea. I don't know. Let's say 4 is Texas. So if I call it a 4 and it really was a 9, it's supposed to go to California, it goes to Texas. If I call it a et cetera,